Let's take a look at an application problem. An airplane heading due west at 325 miles per hour encounters a 55 mile per hour wind flowing in the direction of east 20 degrees north. Whoa, why is that doing that? There we go. Express the velocity v of the airplane relative to the air and the velocity w of the wind in component form. Find the true velocity of the airplane as a vector and find the true speed and direction of the airplane. Okay, that's a lot. But let's just start with the given information and how we're going to draw a picture of that. So we have an airplane heading due west at 325 miles per hour. This is a vector. All right, this vector has direction and it has length, and the length in this vector is going to be equivalent to the speed. Like those, we looked at sort of the wind application, the other day. It doesn't have to be, the magnitude doesn't have to be a distance. Okay, I'm going to try to draw a nice straight line here. Here we go. That's as good as it gets. Okay, so let's say this is the vector. We'll say this is like standard position, and it's headed due west, so north, south, east, west, at 325 miles per hour. 300. So I'm going to make this represent the magnitude, 325 miles per hour. So this is vector v. Express the velocity v of the airplane relative to the air and the velocity w in component form. So this is our vector v. What would be the component form of that vector? All right, I'm assuming like this is the origin here. It doesn't really matter because vectors don't need to be at the origin, but you got it? It would be negative 325, 0. Okay, because it's headed 325 miles per hour in that direction. Let's see if I can make this nice without messing it up. Okay, so there's my axis. Let's do the next one. We have a 55 mile per hour wind, so that's the magnitude, flowing in the direction of east 20 degrees north. So let's talk about what east 20 degrees north means. Let's look at a couple examples over here about directions and bearings. Here's some examples. So let's say we have north 30 degrees east. So that tells you head north, and then go 30 degrees east of that. So this bearing right here would be north 30 degrees east. All right, let's look at another one. Here's the point B. That's north 60 degrees west. So head north, but go 60 degrees west of that. So you'd head along this line. C, if we look at it this way, we're headed south 70 degrees east. We could also say east 20 degrees south. East 20 degrees south would be the same bearing as south 70 degrees east. In this example here, this one is south 80 degrees west, which would be the same as west 10 degrees south. All right, so let's go look at ours. Ours is east. We're going to head east, but then we're going to go 20 degrees north of that. All right, let's do this in blue. So I'm going to go, and it's only 55 miles, so I count at 50 miles per hour. I want to make it sort of proportional to my 325. So this keeps going. So my 325 is that long. I'll make my 55 mile per hour wind vector about that long. And then this in here is 20 degrees. 55 miles per hour. Okay, so now it's asking us to find the components of W. So we're going to do like we did before. We're going to do the x value is going to be r cosine theta, and y is r sine theta. Okay, and so those would be literally the horizontal and vertical components if you start at the initial point and move to the terminal point. Now it's asking us to find the true velocity of the airplane as a vector. So what's happening is the airplane is has its bearings due west, but the wind is blowing this way across the plane. So it's going to push it off course a little bit. So the way we find the true bearing of the plane is we add these vectors together. All right, so we have the plane plus the wind, and this vector is the true direction of the plane, and we're going to find the velocity, which is the speed. So to add these vectors together, we can use the components, but I also want to look at it pictorially. So I'm going to move this wind vector over to here, 55 miles per hour. That is the 20-degree angle. So the actual direction of the plane is going to be like that. Okay, so this is vector v plus w. So that's going to be the direction that the plane will, sorry, this is not great right in here, but hopefully you can live with it. That's a little bit better. So the actual direction of the plane is going to be along the line of this v plus w, and the speed of the plane will be the magnitude of this vector. The velocity, so the velocity, when we talk about velocity, we mean velocity means speed and direction. So that's what we need to find. Velocity. We need to find speed in miles per hour and direction, which is really what is kind of happening down here as well, the speed and direction. So find it as a vector. So as a vector, that's vector v plus w. So we're going to add the x components together of v and the x component of w, and the y component of v, or the vertical component, added with the vertical component of the wind. And certainly we could punch those into our calculator and get some kind of approximation. So if you punch that into your calculator, you get negative 302.6 and 50.2, which seems reasonable for our graph over here. All right, so now we want to find the true speed and direction of the airplane. So let's pull out this vector and just look at it. So let's pull out this true direction and this guy, this v plus w. Okay. So what we need to find is we need to find this angle, and we need to find the length. So I'll call those r and theta. Right? We need to find those angles, or we could find, this angle over here and then subtract from 180, and that will give us the speed and direction of the plane. So again, this is where polar coordinates can really help. If we think about this as polar coordinates, this would be the x and y value, and we're trying to find the angle and the r, which we can use our polar knowledge. We know that the x component squared plus the y component squared will give us that radius. So let's go ahead and do that. Higher mathematics. 9,086.8 is r squared, so we'll take the square root of both sides. Oh, I lost a decimal here. Let's try that again. 94,086. How about that? Does that sound better? 0.8. And the square root of that is 306.7, which kind of makes sense. All right, so that represents the magnitude or the length of the vector, which in this application is being used to model the speed. So that makes sense, right? I mean, the wind is blowing a little bit in the face. It's not a head-on wind, but it's definitely blowing in the face of the plane, and so it's going to slow it down a little bit. I don't know if you've ever traveled, but when you travel west to east, the jet stream usually flows that way. So the flights are shorter. Then if you do the same exact flight going the other direction from east to west, and I'm not talking about time change here, I'm actually talking about literal flight time, is longer when you're moving east to west because you're generally flying against the jet stream, and so your speed is slowed down. All right, so now as far as the direction goes, we need to find this angle, and we can use tangent. All right, we know that the tangent of theta is equal to the y component divided by the x component. And we need to be a little bit careful here with inverse tangent. We're going to get a negative value here if we use the negative. If you want to get real right triangle on yourself, you can just use these as positives and get this x as a positive number. When you're talking about bearings, you're not going to do any negatives. So I can show it both ways. Let's see what this inverse tangent is. Let's do the inverse tangent with the positive and the negative, and then we'll talk about how to use them. But honestly, I would just always use the positive, and then I'm going to have to describe this as north, south, east, and west, and that's really where the negatives kind of come into play as far as what quadrant you're in. So actually, I'm not going to model doing this with a negative in this case because I don't think it's useful. So let's find that inverse tangent. All right, I got about 9.4 degrees, which I think makes sense. We can look at our picture and think about it. It's blowing it off course then is what we're saying. It's blowing it off course here about 9.4 degrees. That seems reasonable. Okay, so now how am I literally going to describe this? Well, the plane is basically heading west, but it's being blown off course 9.4 degrees north. Head west, but a little bit north of that, 9.4 degrees north. So this is the true speed and direction of the plane. I hope you can appreciate how so much of what we've been working on the whole quarter is in this one problem. All right, we've got polar coordinates, we've got inverse tangent, we've got r cosine theta, r sine theta. So much of what we've done is showing up in this one application problem. So really think deeply about what's going on and how these are all connected together, and that will help you to remember these things and to appreciate how they all work together.